What's first? I can't hear you. What's first? I literally cannot hear you because this is a video. But still, I'm being brave by making this my first video. You're being brave by doing this, by taking notes as well. So I want to set some expectations. And as I said, take notes, okay? During all of this, take notes. Be kind to future you. Imagine we're in Black Mode in class. You have your notes out. You are taking them. I'll wait until you get your notes out. Still waiting. I bet you're just watching the video, not doing notes. Please pause the video and get notes. You can pause the video at any time you want. All right, but let's actually get started. Think of questions as well. All right, so what are vectors? The big idea of vectors is that we can think of lines as right triangles. We can imagine a line, imagine it instead of as just a line, we can imagine it instead as a right triangle. And that's simple, and that seems a little bit more complicated to go from a line to a right triangle, but it actually, imagining a line as a right triangle makes the math way more simple. That little bit of complicated imagination will end up making the math way, way more simple. That's actually what allowed us to go from small buildings to skyscrapers, because the math got simpler when we thought of vectors that way. Okay, so let's talk about vector notation. All right. Vector notation, when you see it printed, when you see it in books, when you see it on the IB exam, you're going to see it's going to be a bold V, all right? It'll be printed bold. Obviously, that's really weird to do handwritten, so we don't do that handwritten. Sometimes you might also see it in books as this, with a little arrow like that, like a full arrow. Imagine that's a full arrow. And then, but most of the time you'll see me, if I'm handwriting it, I'll do that. That little, it's like a half arrow. It means an arrow. It means it's a vector. That's the vector V. This right here is the vector A. All right, the vector A. That's the vector V. Here's the vector A. Okay, so when you see those notations, that means they're vectors. If you see bolded letters, it means it's a vector. So, parts of a vector. We've got the head here at the arrow. That's the head for A. The head for V, and then this is the tail, all right? The head and the tail. Those are the parts visually of a vector, okay? And we think of a vector as going from tail to head, okay? It's going in that direction. It's pointing in the direction of the arrow, all right? It has magnitude and direction, just like Vector from Despicable Me says, okay? But we think of those as heads and tails, all right? And yeah, magnitude and direction. Hey, we talked about this. The notation for magnitude is the length of the line graphically. That's how we represent it graphically. So the magnitude is the length of this line. In the notation we use, some people do like this, they'll do a double bar, especially if it's in print, they might do a double bar. Looks like that for the magnitude. I will write it like this on the notation. Notice that looks like absolute value because it actually is absolute value signs. Okay, so when we're talking about the length of the line, it's the magnitude. And these are the notations for it. The direction, when we're talking about direction, that's the angle. And the angle theta always starts from the positive horizontal attached to the tail. All right, so it always starts on this line. All right, because remember in pre-cal and calculus and stuff, we always measure angles from the positive x-axis, all right? So notice these are starting in different places, okay? And that's okay. It's the positive x horizontal direction. Components. This is the important part. This is what really matters. This is what's cool about vectors, that we can transform them from magnitude and direction into components. This is the key right here that allowed us to go from small buildings to skyscrapers, strangely enough. And what we did is, again, we're turning that line into a right triangle. So there's the x component here. X component. And in this case, right there. So x component here, x component here. And there's the y component. These are the y components. Notice the x components are the horizontal components. Notice the y components are the vertical components. Notice as well, with vector A here, notice that vector A is going backwards, so the x component would actually go backwards as well. So this x component here would be negative, okay? So those are the components, x's and y's. So again, notice we're taking the line and breaking it into a right triangle and thinking of these lines as and forces and directions and speeds and or velocities and other things like that as, not speeds, as right triangles. And that's the key right there. So now that we have components, we need to talk about component notation. Notice that the x components here for this triangle, this is 5 for the x component on vector v. The y component on vector v is 12. The x component on vector, it's a negative. Come on, honey. It's a negative 4. And then the y component is positive 3. So there's 3 different notations for this component form of vectors. Okay, there's one, the column form that the IB really likes. Okay, and you just put it in a column. And it's going to be the x over the y. Okay, and then there's sort of a coordinate form. And notice I put the coordinate in quotes. It looks like coordinate form, but it's not. And the key thing it tells you, you're not going to have parentheses. You're going to have like a greater than and a less than that act as the parentheses for the components. And then it's going to be the x, y. But these, again, are the x and y components of the vectors. All right. The other form is going to seem strange, but it's actually the most mathematically important one. You're going to have an x component. You're going to have a y component. But then we're going to have what are called unit vectors. I is the unit vector in the x direction. And then the unit vector in the y direction is j. And we call it, now I put the little caret on top, we call it the hat, okay? It's I hat and j hat. For z, there's also a k hat. We'll get to that next time. But so in component form, it's the x vector times I plus the y vector times j hat. Okay? And then now, for the longest time, I actually didn't even realize this in college. I was very confused why they would use I. Wouldn't that get us confused with the imaginary I? But in fact, it's the same thing. This is the imaginary letter I, okay, corresponding to the square root of -1. Okay, and j is also a different kind of square root of -1. That's really weird. Don't worry about it too much, but if when the math, on the back end of the math, when it gets really fancy, it actually works. And that's actually how we were able to mathematically go, again, from small buildings to skyscrapers, believe it or not. And I never actually realized that in college. So now I'm going to show you what vector v would look like, okay, in component form. Okay, in column, or in these various component notations. So in column form, vector v would be 5, all right, over the 12. Okay, in this coordinate form, okay, it would be 5 and the 12. Okay, and then in the component form, it would be 5 times I hat plus 12 times j hat. All right, that's in component form. For vector A right here, again, just to give another example, okay, that would be -4 over 3. In this so-called coordinate form, this would be -4 and 3. And then in component form, be -4i plus 3j hat. I'll let you know that IB really likes column form, okay? And I can almost guarantee they will give you one like this. And they even do transformations of graphs with column form. Delta Math, on the other hand, and frankly, many of my math and engineering classes had, well, math for engineers. I didn't actually take engineering classes, but had this more of coordinate form sometimes. But everybody uses this because this is mathematically on what's going on underneath. So IB is going to use this and things like that. Confusingly, sometimes I think Delta Math even calls what I'm calling coordinate form component form, and I think Delta Math calls what I'm calling component form the unit vector or the standard unit vector form. IB, on the other hand, calls this the I's and J's and K's component form. So, all right, remember, we're just introducing stuff. All right, moving on. All right, when you're in components, all right, please, a couple things. Do not confuse components with coordinates. Notice that we don't actually have a coordinate grid here. We don't know where it's starting or ending. What matters actually is just the change in the x and the change in the y. And in fact, you can have vectors that are parallel. If I had another vector here that was exactly like v, had the same change in x and same change of y, the same slope, if you would, and the same distance, it would be equivalent as a vector. So vectors are actually without position, except for position vectors, which are a special case. But most of the time, it doesn't actually matter where a vector starts. That sounds really weird. It's actually really important for what we're going to do later on with vectors. So, but yeah, don't confuse the components, okay, are not equal to coordinates. They're kind of like coordinates, but they're not the same thing. If you find yourself getting confused with vectors, that might be what's happening. So the other thing I want to point out is notice in column form, okay, let's say of column form of A, you start always with the x and then you put the y. Okay, notice that if I were to make the slope, which is the change in y over the change in x, that slope would be 3 over, negative 4. Negative 4. Okay? So notice the difference between those. Notice how it could be easy to confuse that. I just want you, so be clear on what your x's and your y's are in this case. So, all right, finding the magnitude. So the magnitude corresponds, like we said, to the length of the hypotenuse. All right, the length of the vector. Well, how would you find the hypotenuse here? Oh my gosh, we could use Pythagorean theorem. Oh my gosh, yes, that's exactly what we do. Okay, so if I'm getting the magnitude of v, all right, that's going to be the square root of the x component squared. Okay, plus the y component squared, right? Because it's the absolute, I mean, it's just Pythagorean, y'all. So in this case, the v, if we remember our Pythagorean triples, is just 13, the magnitude of v. All right, and the magnitude of a, in this case, nope. Is just 5. So that's it. How do you find magnitude? Pythagorean. So if they ever tell you to find magnitude or find this with the absolute value or whatever in some way, shape, or form, you need to be thinking Pythagorean. All right, that's how you're going to do it. And that's the end of this recording. The next part is going to be about what to do with the delta math.